Okay, in this video I'm going to look at another rate of change problem. This one's a little bit different because it's not a velocity rate of change. So in this example we're asked about the volume of a cube, which is given by the equation v of x, if you want to write it in function notation, which is equal to x cubed, right? Volume of a cube is equal to the side length cubed, where x is the side length. In this case we're going to measure it in centimeters. We want to determine the average rate of change in the total volume of the cube when each side length increases from 4 centimeters to 5 centimeters. So in this case, we don't want the rate of change as with respect to time. We want it with respect to side length. So you've got your cube. So what's happening is this cube is growing. I don't know how fast, and I'm not asked about how fast. What I'm asked about is how much the volume is changing with respect to side length. So what I want as a rate of change is the change in volume, not over time, but over the change in the side length. So it's the average rate of change. So you need an interval, and the interval is just 4 to 5 centimeters. So between 4 and 5 centimeters. So we want the volume at 5 centimeters minus the volume at 4 centimeters divided by 5 minus 4 centimeters. So the volume at 5 centimeters, that would be just the 5 cubed, minus the volume at 4 centimeters, which is 4 cubed, all over 1. 5 cubed is 125, minus 4 cubed is 64, over 1. So this works out to 61. And now the units, so the numerator of the units was volume. So that would be centimeters cubed divided by the units for the denominator, which was centimeters. So centimeters cubed per centimeter. So what this means is as the volume, as the side length increases by 1 from 4 to 5 centimeters, so 1 centimeter, the volume is increasing by 61 centimeters cubed. Okay, so that's the rate of change. So therefore, the volume increases by 61 centimeters. Let's say at a rate. No, it's 61 centimeters cubed per centimeter as the side length increases from 4 to 5 centimeters. So one thing just to note here is the units here, you have centimeters cubed per centimeter. You can't reduce that, right? Like that's centimeters cubed over centimeters. Even though they're both centimeters, you can't reduce that to centimeters squared, because then you'd be losing the whole concept or the whole idea of this being a rate of change. We want to see how fast the volume changes as the side length changes. Okay, so here's a second example. Same cube, which is increasing, but it's an instantaneous rate of change question. So we want the instantaneous rate of change when the side length is 5, or when x equals 5. So here we have to, we're still looking for the rate of change of volume with respect to side length, but we want the instantaneous rate of change, so we need to use that limit definition. The limit as h goes to 0. Here we're looking at the volume function, so h plus the time, or the instant, in this case the side length 5, we were looking at minus the volume at 5, all divided by h. So we just need to substitute this into our volume formula. So the limit as h goes to 0 of h plus 5 cubed minus 5 cubed, all divided by h. So here you have to expand this binomial, which is being cubed. So that can take a few steps, or if you remember the binomial theorem from grade 11, it's a little bit simpler. If you remember the binomial theorem, this is going to be, the first term is going to be this term cubed. The next term is going to be, if you remember Pascal's triangle, these were the coefficients when you square a binomial. These were the coefficients when you cube a binomial. So the first one had a coefficient of 1, which is why it's just a 1. The second one has a coefficient of 3. So it's going to be 3 times this term here times this term squared. So it'd be 5 times h squared plus, and then it's another 3. And now you just flip it. This one times this one squared. Plus this one, this last one cubed. So 125. So that's the first bracket there, all cubed, minus 5 cubed, which is 125. If you don't remember the binomial theorem, you can just sort of expand it the long way and you'll see you'll get the same thing. So limit as h goes to 0, so this would be h cubed plus 15 h squared minus 75 h plus 125 minus 125, all divided by h. 125 and the minus 125 will cancel out. You got a common factor of h on the numerator. Don't worry about any constants. H squared minus 15h minus 75. Oh, sorry. It wasn't minus, it was plus. This should be plus. And there's no h. Common factor of the h. Okay, so then this h and this h will divide. You'll have the limit as h goes to 0 of h squared minus 15h. Oh, sorry, again, that should be a plus. Won't matter, it's going to go to 0, but it should be plus. So now it's the limit as h goes to 0 of a polynomial. So we can use direct substitution. So that'd be 0 squared plus 15 times 0 plus 75. So you get 75, and the units are the same as the units from that first example, centimeters cubed, because the numerator was a volume, per centimeter. So that's the change in volume with respect to x. So that means that the volume's increasing at a rate of 75 centimeters cubed for every 1 centimeter that the side length increases at the instant when the volume is, or when the side length is 5 centimeters.